Right, so hi everyone. Today, as Carlos was saying, I'm going to tell you about chaos in deformed SYK models. And this talk is based together with my postdoc, Saskia de Mulder, and my student, Osher Shoval, and with Damian Galant and Sam from King's College in London. So let me start with a bit of motivation. So why would I be in the first place in studying chaos in deformed SYK models? Well, the obvious motivation, there are two parts to this motivation. This part has to do with the quantum many-body systems that we would like to understand better. Some of these systems are chaotic and some of them are integrable. And in fact, even let's say chaos in many-body quantum system is kind of a subject of debate. Signatures proposed for defining that. And I will mainly focus on two of these signatures, which are the out-of-time ordered correlation functions and Krylov complexity, and I'll define everything. Part of the motivation comes, and I think that's common to many of us, from attempts to understand quantum gravity and the holographic correspondence. And in this context, SYK is famous because it's dual nearly anti-de Sitter 2 space-times. So in this sense, it provides some topic model of space-time. And so it's very natural to whether small changes, different versions of SYK, can extend this very, very specific type of duality and give us more rich space-times, and in particular, I'll come back to that at the end of my talk. Okay, so yeah. So after this slightly longish motivation, I'm going to start a bit of background about the SYK models and what do I mean exactly by talking about the of it. I'll introduce different signatures in quantum many-body systems, and then I will show you some results for signatures of chaos in these deformations of SYK, and come back to the gravitational motivations towards the end. All right, so the SYK model. So the SYK model is a model made out of n Majorana fermions. It's a disordered model, so it's not one model, it's an ensemble of theories where the Hamiltonian is constructed using random couplings, these J's, that are sampled from a Gaussian distribution, mean, and the specific variance, which is uniform among fermions. And typically, each term in the Hamiltonian contains Q fermions out of the n that are available. And this is very interesting because it's both in certain limit exactly solvable, also maximally chaotic, and I will say exactly what that means at low temperatures. It has a specific case, which is the case with two fermions in each interaction term, so basically like a fermion mass term, which is integrable. And from the condensed matter perspective, it's also very interesting because it's used to model strange metals, which are many-body quantum states with quasi-particles. All right, so I said that one of the reasons why this model is remarkable is that it's exactly solvable in certain limits. And in particular, I'm talking about the large n limit. So when I have many fermions, in that case, the partition function for the model can be written in terms of effective degrees of freedom, which are the bilinear fermions and the self-energy. And one can write for them an effective action, and this effective action is much more accessible than the model, the original model, since the original model is built from matrices exponentially with the size of the system, so that becomes unmanageable extremely quickly. And if I'm trying to solve equations of motion coming from an effective action of two functions, then I have to solve some integral differential equations, but that a complete different order of magnitude of complex of being a complex system. A first Another occasion arises when I not only take the available number of fermions n to be very large, but also the number of fermions in each Hamiltonian term to be very large, with a specific ratio kept between these two quantities. That's famous as scaled SYK, but I'm actually going to take first the number of large and only then the number of fermions in each Hamiltonian term to be large. So that for those familiar with double scaled SYK is the limit of this lambda going to 0. But that's going to be rich enough to tell the story. Ah, sorry. All right. Another remarkable property of SYK is that at low temperatures, it's nearly conformal, and that means that it's a fixed point where each one of the fermions has an effective conformal dimension of 1 over q. Q was the number of fermions in each Hamiltonian term. And so then essentially is given by a conformal action plus a correction, which is Schwarzian-like, built from the zero modes of the effective degrees of freedom of the previous action. And in this limit, the model is maximally chaotic. So it attains the maximal rate of perturbation spreading. I'll say what that means in a second. All right. As I said at the beginning, there is a dual gravitational interpretation in JT gravity, which means gravity plus dilaton. The bulk theory is just a rigid ADS2, and so the dynamics effectively to the dynamics of the boundary mode. Yeah. All right. So then, knowing all that raises an okay, it's nice to have rigid ADS2, but what more can we do? Can we have a little bit more rich gravitational background by playing a little bit with the SYK models? And the answer is yes, but it's not, because what you would like to do to get a slightly richer gravitational background is typically deform the interior of the model, like add something by R, but building relations of the SYK model is non-trivial. So the reason is the following. So what would you think would be the natural thing to build is, the obvious thing is, let's take go to the first fixed point, take two fermions, contract them together. Typically, one wants to also preserve the ON symmetry of the model, so psi I, psi I. That doesn't work because they're fermions, so that's 0. And then the next best thing is a time derivative, but that's already irrelevant because each time derivative adds one dimension, and the fermions already have a dimension around, so that's irrelevant. But the one thing that you can do is add SYK Hamiltonian disordered, another disordered contribution. So to take an SYK Hamiltonian with Q fermions and add to it another SYK Hamiltonian with Q fermions. And that thing, as long as Q tilde is smaller than Q, is going to be, at least with a naive counting, relevant. And so it's going to be a deformation which becomes important in the infrared, and it's going to change the background in the interior. Right, okay. And it turns out that basically all the tricks that I told you about before, like taking the large n limit or taking the large q limit and all these things, are also relevant here. The very similar simplifications to the model with the deformation. So in particular, effective action in terms of bilinears can still be written, and effective motion for them can still be written. They are just changed a little bit by these red terms that you see on the slide. And furthermore, you could large q limit, in this case both q and q tilde, with a fixed ratio between, and in that case the equations have an analytic solution. So all the simplifications persist. And that's it more or less. So I'm going to tell you in a second what I'm going to do with this model, but just to recap before I say what I want to study about this model, what I expect. So I expect, if I look at a Hamiltonian, which is an SYK Hamiltonian deformed by another SYK Hamiltonian with a different, smaller number of fermions, I expect that in the UV, when I go in the very fine details of the theory, I'm going to have a free. That's true for the SYK as well. When I slightly zoom out, scale of the random coupling, this J tilde, I'm going to see the immediate phase where the Hamiltonian with Q fermions is going to dominate. And then if I zoom out some more, assuming that really there is a separation, so assume the coefficient of the deformation is small, I'm going to see a deep infrared regime starts to fill the Hamiltonian with the Q tilde fermion. So I should see, I naively expect, is two regimes of maximally chaotic theories. And the question of this talk is going to be, I see that. How can I diagnose that along the flow, so by changing the temperature, I am able to see two regimes of nearly maximal chaos. And for that, I need to tell you how to diagnose chaos, how to define chaos. So for the, I don't know. I've had the chance to ever talk with a condensed matter physicist about quantum chaos. It's heated. It's everyone thinks it's something else. So I'm going to stick with two definitions, and I will tell you the motivation for those definitions. So the first one requires having a semi-classical limit. So at large n, it makes no sense when I'm away from large n, and that's the idea of the out-of-time order correlation functions. And this draws from basically our classical idea, which is hypersensitivity to initial conditions. I change a little bit the inputs of my system. The final outcome changes a lot. In other words, nearby trajectories diverge, and they diverge exponentially. And the exponent, so you see dq of t by dq of 0, the exponent of some exponent, and that exponent is called the Lyapunov exponent, the famous butterfly effect. Now, if I'm in the semi-classical limit, then that deviation with respect to initial condition has a natural analog. Since it can be written in terms of Poisson brackets, it's just analog. The quantum analog is the commutator. So that's something that would, in the semi-classical limit, collapse back to hypersensitivity on initial condition. And so basically what you would naively expect is that essentially commutators of two operators, one at time t, one at time 0, should diverge exponentially. There are a few ingredients to add to this if you want to do this in a quantum mechanical setup. First, one needs to take an expectation value within a certain state. That's usually taken to be state. And furthermore, often naively taking expectation value can have phase cancellations. So what people do is they take the square of that thing. And the square of that thing is essentially 4 point functions of 2 at time t, 2 operators at time 0 out of the time order, and that's the out of time order correlation. And that thing in chaos is expected to indeed behave with an exponential. So it's expected to have two terms that compete with each other that can only be separated when there is a small parameter, say large n. And that's the behavior over there in the square. So it's a constant minus an exponential behavior. It's not quite, it's a related quantity to the one I slide, not quite the same. And that's something that people compute. So they compute the expectation value of operator at time t, operator at time 0, and another time the operator at time t, another time at 0, and read from it the Lyapunov exponent. Read the famous bound on chaos by Maldacena. So it should be bounded in all physical systems. Pi over beta. That's maximal chaos. That's what I say. When I say maximal chaos, that's what I mean. And as I said, you need a semi-classical separation to the different terms, so to even define that quantity. The need to have a large n limit made people unhappy, so they look of chaos in systems that don't have a semi-classical limit. And led to defining this new guy. That's like last 4 years. A very big surge of interest in this new signature, which is Krylov complexity. And the idea is essentially a new signature which estimates, tries to estimate if the system is chaotic by looking at the spread of a perturbation. So you take a system, you put in a perturbation at a specific location, and then you start evolving the system with the Hamiltonian. And you ask, how does this perturbation spread? And one way to estimate that is to notice that the spread or the operator evolved to time t can be constructed by a basis of operators and nested with the Hamiltonian. So the original operator, its commutation with the Hamiltonian, its commutation with the commutation of the Hamiltonian, and so on. And the idea is that the more the Hamiltonian you add, the more complicated is your operator. So what you really want to know, a weighted version of how many of these operators do I need, so that estimate how complicated the operator became at time t. So that's the quantity that you see. That's the SYK of t. The Krylov complexity is essentially n is the number of the operator in this chain times how much of it do I need to build my time-evolved operator. And that thing was conjectured to also behave in a quantum chaotic system with another lambda k, the Krylov exponent. Okay, and as I said, the nice thing is that there is no need for large n in this approach. And it's much easier to compute. So this I didn't say, but somehow by manipulating a thermal two-point function of a theory and doing fancy things, one can get that without ever computing a four-point function. So it's a much easier thing to compute. All right. Few bounds were proven about this new exponent. It bounds above the Lyapunov exponent. It's always smaller than the bound of chaos. And in several cases, in particular in SYK, it's exactly equal to the Lyapunov exponent, which is kind of a magical thing. And that led people to think, maybe we can, not compute four-point functions are a mess. Let's just compute this Krylov guy. As a way to measure chaos, we're going to see this exponential behavior, that it's chaotic or maximally chaotic or whatever. And so that brings me back to my story. So now we wanted to use these two signatures if the flows SYK, if they are chaotic or not, if they have of chaos, which of the signatures can diagnose that. So the questions to answer are, what are these lambda L and lambda K in deformed SYK models? Are they equal to each other? And can they both diagnose chaos or chaos transitions? And everything I'm going to be at large n, of course, because if I need to compare one thing that is only defined, I can only do that. All right, so a few first results are expansions. So at n goes to infinity, q goes to infinity, that's the limit where the solutions are analytic. The values of the two exponents are in fact the same, and of course by all the bounds that I showed you earlier. But as soon as you go away, as soon as you have a finite number of terms in your a finite number of fermions in each Hamiltonian interaction, that's no longer true, and there is already a small deviation the two exponent, which is of order 1 over q and 1 over the temperature, and proportional to the temperature. But a much larger deviation can be seen when you start exploring. So that's, I would say, one of the main plots. So here there are Hamiltonian with q fermions, Hamiltonian with q fermions, and q is taken to infinity. So there is, I do expect of nearly maximal chaos, and that's actually what you kind of see in the figure. So the figure has two lines. One is orange, that's the Krylov exponent, and one is dashed black, and the exponent coming from the Otok, the Lyapunov exponent. And you see that, let's start with the Lyapunov exponent. So as I decrease the temperature, increase beta, as I flow to the infrared, I free, so with very small exponent. It's normalized so that maximal chaos is at 1. So then I see a region of near maximal chaos, then a transition, and then another region of nearly maximal chaos. But the interesting thing is that the Krylov exponent doesn't see any of that. So we're not a very good signature of chaos, at least in these. But we do see, we do, by using the Otok, see these transitions. Good. So that's one thing. Sorry. And the next thing we wanted to do was to look at finite finite Q, so not infinite Q. The limit where theory is not requires a bit of numerics. So for example, 6 fermions deformed by 2 fermions, or 6 by 4. That's very useful because you can have anything deformed by 2 fermions. You can have chaotic integrable transitions. And so these are a bit of details of the numerics to convince you that there is some work into it. So what to do is basically take the Schwinger-Dyson equations, which are those that give us the linears, rewrite them in Fourier space using a spectral density, and then solve with some iterative procedure when one solves one equation in position space, then one in momentum space, and back and forth, to extract the two-point function in various continuations in Lorentzian time. From the moments of the two-point functions, which are essentially related to the different amplitudes of the operator in the Krylov basis that I showed earlier, we can get the Krylov exponent. Then then the 4-point function comes from some kernel equation that one diagonalizes using big matrices. So that's kind of a heavy numerical procedure, especially hard at low temperatures. Okay, but we had some nice, good students to do all the programming. And I show one more plot. So there are many more plots in the paper, but I chose this one. So these are chaos to integrable transitions. Start with one Hamiltonian. Again, it's at large n, but in each Hamiltonian term there are 6 fermions involved, plus a deformation with a small parameter. With the Hamiltonian term, there are 2 fermions involved. And as I said earlier, the 6 fermion is expected to be chaotic. The 2 fermions, on the other hand, is expected to be integrable. So what one expects is to see a developing of chaos and then back integrability. And indeed, that's what you see in the figure from the dashed purple line, which is the Lyapunov guy. Not extremely visible, I think. But and on the other hand, the one just doesn't see anything, keeps going up, nothing special happens. So we see that also in this example, the Lyapunov exponent sees the transition, while Krylov exponents don't seem to be able to diagnose this type of flows. There is only one case for some hint of possibly Krylov being able to diagnose something, and that's the case where one takes with infinitely many fermions, so that's Q goes to infinity limit and deforms by fermions. It's not that the Krylov exponent dives back to an integrable regime, but just at some point the behavior stops being exponential, and so it's like more or less around the same point where the transition happens for the Lyapunov exponent. Also, the Krylov exponent does something weird. All right, so I'm gonna do a small recap of the, and then I'll say a few words about gravity. So we saw deviations between the two type of exponents meant to diagnose chaos. These are the Krylov Lyapunov exponent coming from the OTOC already for the single SYK. For most cases of flows, of flow SYKs, the Krylov provide a good diagnostic of chaos transitions along RG flows. And in all examples, the Krylov exponent seemed, when it could be defined, to grow monotonically. So that's maybe a conjecture for quantum systems. And now let me go back to talk about the relation to space-time. So we know that K, at least in the low energy limit, is dual to ADS2 space-time, that I said at the beginning. Now, the dual space-time to deformed SYK is also rather well understood, and it's actually dual to an infrared deformation, where one takes an ADS space-time and roughly, not in an abrupt way, a continuous way, changes its interior to be another ADS2 space-time with another cosmological constant. This relation is rather well understood both from the point of view of the thermodynamics of these spacetimes and from the point of view of the Schwarzian action. So different calculations were made to do the exact matching to understand exactly what dilaton potential one would need in JT to exactly get the model to these SYK flows. In 2D, there is another interesting fact, which is very special to 2D, so it doesn't work this way in higher D, is that one can also, instead of slicing a small chunk of the interior ADS and replacing it by with another cosmological constant, is to throw away this interior and replace it with a chunk of the Sitter space. So there are constructions. Possible in 2D in a much more obvious way than in higher D is because of some focusing theorems that are not limiting because there is no spatial sphere. And these geometries have been constructed. So geometries with an interior de Sitter with the available and an exterior ADS in 2 dimensions. And that's very appealing is that many people have tried over the years to talk about the topography, and one of the main roadblocks are the fact that we don't have a time-like boundary on which to put the field. But of course, once you put an interior de Sitter, but the exterior is still ADS, this exterior still has an asymptotic boundary where the field theory can live. And so it really does beg the question of whether these models are described in terms of some type of flow SYK. So it's a change of the interior of a gravity setup with where the exterior looks like ADS2, so probably an SYK, and some interior deformation that creates a de Sitter. And it's not exactly those flows that I was telling you, but we have some hints for what could be the dual theory. And the hints come from, so how do we try to look for a dual theory? In these cases is to begin by looking at some of the properties of the ground. So test, I don't know, the thermodynamics, test react to shock waves, test properties of the gravity background and ask what properties do you expect from the would-be dual field theory of this model. And some things has been done, but most interesting is the fact that when one studies thermodynamics in those de Sitter bubble style geometry, one finds actually the dynamics would have matched a flow SYK with a complex coupling. So HQ plus IS HQ tilde. Okay, doesn't mean that we know what that means, right? Because we obviously like to work with Hermitian Hamiltonians. But non-Hermitian Hamiltonians do appear in the context of open quantum systems, in the Lindblad equation and so on. So, so that might be a hint to think that the Sitter bubbles are dual to open quantum systems because they can evaporate behind the cosmological horizon and just go to SKY plus. And so, yeah, so that's just a hint towards perhaps some type of flow with some type of open quantum system could be dual to this de Sitter bubbles, but the answer is that we don't know. That it's much less understood than just the flow, but this is just to give motivation. That could be interesting. A lot of work has been done about chaos in our system, so it would be interesting to make this connection much more precise. Yeah, I think that's it, more or less. That's what I wanted to.